Resiliency, and we also have another tool called CPSAM, which we're almost close to being done. We are going through our final validation checks and all that. And we are also in the next stages, or some of the work that I'm going to be presenting today is about the resiliency metrics and assessment tools for the electric transmission system. So bringing out the differences between the smaller microgrid and distribution system to the transmission systems. And our team at Rutgers are working towards the resiliency of controllers and PLCs. They also already have a tool out. It's called TSV, Trusted Safety Verifier. Professor Zanuz had a great presentation at the recently concluded industrial workshop, and we'll also be touching base with that project a little bit. And then finally, our end goal is to kind of put everything together, which is to enable operational resiliency by combining all the different tools for microgrids, distribution system, transmission systems, and also the devices and the controllers and the PLCs. So that is going to be some of the things that I'm going to be talking about today. So the metrics framework, so this work has been going on, I would say, almost since the start of GRETC. So it's kind of in a good place right now. So the way the metrics framework that you see here is basically like a 4 or a 3-step process. So we start off with data from a cyber physical system architecture, which would be the power system layer, the device layer, the communication layer, the management layer. So based on the data that we obtain from all of these different layers, we're going to be creating a CPS model, a resilience-aware CPS model, and we'll be taking in static data, which is to say topology data and things that don't change in operation. And we'll also be including more real-time measurements and real-time data from all of the different systems. And those things put together will be the basis for our CPS, resilience-aware CPS model. And we will also be looking to derive certain parameters and certain values from these systems. So once we identify the factors that contribute to resiliency for these different systems, we'll be assigning weights for each of these different values and then combining them using multi-criteria decision-making processes to obtain our single resiliency metric. So this resiliency metric is more of an operational real-time metric, which would change according to the data that's coming into the model or coming into the metrics engine. And it is not a historical-based metric that would look at failure rates and others. So it's a different real-time operational resiliency metric that we're looking at. So there's more details in the figure about different systems and say particular MCDM techniques such as like fuzzy Choquet intergrid. So, but the overall metrics framework remains constant or remains the same across different systems. And we'll be talking more about each of those different steps today. So, so I would like to focus more on the cyber system resilience because we've already kind of talked about the physical system resilience a little bit before, especially in terms of the microgrid and the distribution systems. So I'll be touching on that, but if you have any questions, do feel free to ask me, and we can also talk about it offline, or we can share our papers with you. So just zeroing in on the cyber system resilience. So our cyber metric actually integrates 2 different components. One is an attack graph metric component, and 2 is a measurement-based operational component, similar to the breakdown that you saw in the previous slide. So one of the key challenges is to model the cyber, the communication, the physical system, and also all the interdependencies between these systems. So how do we do that? So the cyber model, in our opinion, needs to incorporate 2 key properties. One is the interdependency between the systems, and 2 is to understand the impact from a cyber attack on the different systems. So given a cyber topology or given a cyber system, what is the area of impact for a particular cyber attack? So these are the 2 things that we are looking to derive from our cyber model. And that is the basis on which we create our on which we make assumptions about the cyber model. So the first assumption that we make is that the cyber model, to put it in another way, the power system graph is a minor of the communication graph. So meaning the cyber model is assumed to be an isomorphic bijective relationship between these two graphs, which is just a way of saying that they have a one-to-one mapping relationship, but the cyber model is allowed to be a little bit more detailed than the physical power system model. So what do we mean by that? So in this figure, you see three different layers. One, the one at the bottom of your screen is the physical power system layer, and it is a very simple system. It is just a generator that is connected to a load through a transmission line. So that is the basic sort of power system layer that we're working off of. But the cyber model for these different devices or these different components is in the layer above that. So which is to say the generator usually has some sort of a machine control unit, and which would control the different devices or the processes, such as the machine, the turbine, the valve, and there might be other set points. There might be also auxiliary devices such as exciters or governors. So the machine control unit, so the generator itself is a very complex component that has a lot of devices or processes that is built into it. So this is why we have a one-on-one relationship, because the whole of the generator in the physical power system is mapped onto just one block in the cyber system, but that one block has a lot of different processes that allows us to consider vulnerabilities and risks in terms of the different processes and devices in that particular unit or particular component. And similarly, we also have a load module, which has basically two blocks, which is a measurement block and a control block. So the measurement block would allow you to sense and send measurements about the status of the load. The control, if there is any present, would allow you to control the load, turn it on, turn it off, or if there is some sort of a demand response, you can step down the value of the load. So these models are kind of the basis for the cyber system. And then for the transmission lines, we also model that using the communication system, which is at the top half of your screen. So there can be different ways in which we can model the communication, or in which we can model the exact structure of the communication. There can be different topologies, and we've assumed that there can be firewalls between different nodes, and there can also be certain DMZs that can allow you to have some separation between IT and OT technologies, and so on. So this is kind of our cyber model mapping that we've created, and which we will use to understand the interdependencies between the different systems, and also to understand how what is the impact for a certain vulnerability or a certain cyber attack. And also there can be some cross-domain exploits between these different nodes or these different cyber systems. So that is another thing to consider in the model. So to understand the impact of a successful exploit, we've used the concept of reachable machines. So as said before, in addition to the different processes in the physical node, there's also communication links between these different nodes. So in order to determine the impact of a successful cyber exploit, we use this concept called reachable machines. So it is assumed that the reachable, or the definition of a reachable machine, is any machine that the user, or in case of a cyber attack, the attacker has access to without needing any additional security privileges. So if you consider the whole communication graph to be GC, then the smaller subset of the graph, GS, which is like shown on the figure to your left. So those are all the reachable machines that you can get to without needing any additional security privileges. So this model allows us the flexibility to model regular operation, meaning it also helps us to define what security privileges is needed for an operator to access certain devices in the model, and also it allows us to track how much security privileges an attacker has occurred over a period of time, and that allows us to kind of understand what is the impact of a certain exploit or a certain vulnerability. So based on the models we've defined, we've kind of defined two other metrics. One is the exploitability and one is the reachability. So the exploitability is very simple. It is based off of the CVSS formulation, which stands for Common Vulnerability Scoring System. So what that is a qualitative measure of various vulnerability information. So CVE stands for Common Vulnerabilities and Exposures. So the CVSS is a method of scoring a particular vulnerability. So we've kind of summed up the exploitability scores for the different CVEs that are present in the network, and that is basically, in effect, the exploitability score. And the reachability score is again scaled between 0 to 10, as also scaled in the CVSS formulation. So based on the previous graph, we've seen that RD is the number of reachable devices, and the NRD stands for the non-reachable devices that exist in the system. So the reachability metric is basically a metric that tells you how many machines in your network are reachable from an attacker's standpoint. So these are the two metrics that we've kind of developed for the cyber side of the formulation. And so in addition to that, we also have measurement-based metrics. So we look particularly at, say, latency, which we kind of simulate using different communication system simulators. And we have the latency between various nodes and the time it takes to actually communicate a control signal from point A to point B. And we also look at other topological metrics from the graph, including average path length and also a matrix redundancy metric that allows us to understand the nature of the communication graph better. And finally, all these parameters are combined with our physical metric to obtain CPSAM, which stands for Cyber Physical Security Assessment Metric. So just a brief overview of what that is. So this is like a flow chart of how we calculate that metric. So we determine the factors from various domains that affect resiliency. So in the past few minutes, we've talked about the different cyber parameters that affect the resiliency, and we also have a bunch of physical parameters that affect resiliency, including, again, various topological based metrics from the graph or from the physical power system graph, and we also look at various physical constraints, including power flow, voltage constraints, and so on. So we combine, or we determine the factors from these various domains that affect resiliency, and then we assign the initial weights for each of these factors. So in the fuzzy Choquet integral, which is what we use for determining the microgrid resiliency, we have to determine a fuzzy weight for a combination of different factors. And once we have those fuzzy weights, we determine an interaction index for each scenario. So for each scenario, such as, say, a DOS attack or a compromise on a certain device in the system, not all the factors would be affected. So we have to determine an interaction index that would tell us which factors contribute the most towards a particular scenario. And once we have those numbers in place, then we can combine these parameters together using the Choquet integral process, which is a weighted average, and then we get the resiliency value for each scenario. So this is the overall process by which we get the CPSAM metric. So some of you might be familiar with the graph that we've presented before, and so this is just the way that CPSAM looks for different use cases. So you will not be usually seeing all of these graphs in the same on the same figure, but for example, you would do we did a case which was inspired by the Chaos Monkey tool by Netflix, which is to randomly remove a subset of the graph and then observe how the system would react to it. So we are using the same metric methodology that we've talked about, and we've used a reconfiguration algorithm to kind of stabilize the microgrid once the attack happens. So as you can see on your left, the microgrid's resiliency value is somewhere around 80 or 85 in normal operation, and then we have, say, a random failure which would remove a subset of the graph, and once that action is performed, the physical reconfiguration algorithm would kick in, and it would reconfigure to the most resilient configuration given the particular scenario at that point. So that's why the resiliency would go back to some sort of a degraded operation. And and the CP-SAM is basically a tool that enables you to kind of understand why resiliency is decreasing at any given point of time, and enable you to take appropriate control actions based on the increased visibility that it provides. So moving on to another domain or to another approach for determining resiliency, we have been working this quarter mainly on the transmission system resilience. So some of the challenges in determining the resiliency for a transmission system is the transmission systems are mesh networks and not radial, unlike the distribution systems. So the mesh networks creates redundancy in the network paths. So we cannot use the shortest paths, which is a characteristic of the distribution system that we've used. So, and also transmission systems have multiple sources of power supply and different redundant systems. So we have to take that into account while estimating the resiliency. And also in the distribution system, we have certain node or load points that we've defined to be critical loads. But in the transmission system, all of the buses or all of the load buses would probably have some percentage of critical load. So that is the assumption that we are making, that all buses have a certain percentage of critical or priority load. So the effort needs to be such that we need to ensure power supply to all possible loads, but maybe degraded with a degraded load capacity. And so the resiliency of the power system does not also stop at the transmission level. So to ensure the fidelity of the resiliency calculation at the distribution systems, we have to ensure that the transmission system is also resilient. So, or we need to take into account the changing resilience of the transmission system while monitoring the resilience for the distribution of the microgrid systems. So it's a top-down process that needs to exchange data between these different systems. So those are some of the challenges that we've encountered in determining the transmission system resilience. So this is our kind of our overall structure for the physical resilience in the transmission system. So like we discussed before, it's a little different than the distribution system resilience. So to your left, going from left to right, we have some graph theoretical notions or some topological factors, such as the sources or the different sources, the number of redundant paths between the source and the load. And we have also two new metrics. One is the branch vulnerability and also the number of branches. And also we have some operating condition metrics such as megawatt availability, the megawatt availability, and the loss of load index. So again, we go back to our net metrics framework, which is to combine all of these metrics together using the MCDM approach, which is to have weights assigned for all of these different factors and then combine them to get a single resilience value. So the figure explains that we have 4 graph theory-based indices, and then we have some measurement-based indices. So what are these different terms that we've used? So the first one is the source path destination index. So the reason why we calculate the SPD index is to take into account the network configuration and redundancy in connectivity based on the physics-based electric power flow. So which is basically to say that it is a topological metric that tells you or that defines the connectivity between source and the load, and it details or it quantifies how well a destination or how well a load is connected to the different sources in the transmission system. So this approach it works better because if you want to determine all the shortest paths from all the different sources to all the different loads, this becomes computationally very expensive. And since we are positioning this metric to be a sort of real-time operational metric, we needed something that is faster in terms of computation. So So in this study, we only study the k shortest paths between between the source and the destination. So the SPD index, so that is the formulation, and we'll talk about, or we'll break down each of the terms that you see there. So talking about the k shortest paths, right? So how do we actually determine the k shortest paths? Which is to say, we created a weighted network graph, and we find out the number of k paths from the source to the destination. And once we hit a tolerance in terms of the average cost of the path, so then we cap off the k shortest paths at that point, and we don't determine more paths at that point. So for to understand that concept better, we use the IEEE 14 bus system. So at a specific point, the average of cost. So when your number of paths becomes higher and higher, which is to say around the 15 or 16 path point, then the average cost becomes infinite, and then as the number of paths increases. So we try to cap off the number of k shortest paths based on that tolerance. So instead of having, say, 50 or 60 paths, we cap it off for each bus at 17 and 16. So that is the k shortest paths, and just to go back to the SPD index, so that is the k is the term at the top of the equation, or in the numerator of the equation that you see. So moving on to the other two indices or metrics. So the first one is the branch vulnerability index, which is to say, so if you consider a path between a source and a destination, the BVI index is a way of quantifying how many times a particular segment of the path or particular segment of the line is repeating across different paths. So if you consider, for example, in the k shortest path, say there are 16 paths, and there is one particular segment that's present in all of the paths, so that means that particular segment's importance is pretty high. So that is the branch vulnerability index, which allows us to quantify how important a particular segment of the path is. So the BVI is given by the formula that you see there. So the number of times a particular path or a particular branch occurs is basically the NK by P, and K is the number of shortest paths, and P is the number of parallel lines in a multi-circuit line if there exists a multi-circuit line between two in a segment, then that is also considered or incorporated into the equation. So moving on, we have an example for the BVI. So consider that you have a 5-bus system, bus 1 through 5 that you see labeled there. So the number of points, for example, if you see for going from bus 1 to bus 4, which is the load, so you have two different paths, but you can see that certain segments are repeating, which is to say the segment between bus 1 and 2 is repeating. So that is why that particular segment is vulnerable, or is considered to be more important than the other sections. So this is a very simple illustration of what the BVI attempts to do, or what it attempts to quantify. So the next index is the hops index, which is to say the number of links in a particular or the number of segments in a particular path. So if you want to go back to the previous example, let's say between bus 1 and 4 there is one segment between 1 and 2, 2 to 3, and 3 to 4. So that's 3 different hops or 3 different segments. So it is basically a measure of the number of hops between linking a source and a destination. So the formulation or the equation is given there, and the NLK is the number of hops in the k shortest path that goes from the generator I to the destination substation. So for the previous example, we have the hops index to be 3 for the 2 different paths that is in the system. So this is the overall SPD index for the 5-bus system, the 5-bus example that we've seen. So for the different buses, you have different cases that we've simulated. So on your left, you see the various cases. So at the bottom of your screen, you see the base case, which is the SPD index for the base case. And considering if there is a line outage between buses 2 and 3, the SPD index decreases. And we also see that the metric will increase if there is more redundancy built into the system, which is to say if the one line between 1 and 2 is a multi-circuit line, so the resiliency or the SPD index increases, and if there is an additional generator or an additional line, again, the redundancy would increase or the SPD index would increase. So these are all the topological metrics, and we also combine them with the sort of the physical metrics or the electrical indices. So the first one is the megawatt availability index. So you have the megawatt availability, which is to say if a generator is rated at say 1000 megawatts and it is generating only 500 megawatts, you have 500 that is kind of available to you in reserve. And the generator availability is a notion that helps you understand how reliable a particular generator is. So, for example, a nuclear generator or a hydro station would be probably more reliable than, say, a solar or any sort of renewable generation. So this is the megawatt availability index, which is the combination of the reserve that you have, the type of generator that is providing the reserve, and the total megawatt load. So that is the megawatt availability index for the system. And the megawatt availability is somewhat similar, which is to say the megawatt that is available in reserve in your system by the total megawatt load. And since most of the megawatt devices, which is to say the capacitors or the synchronous condensers, most of them have a similar sense of reliability. We don't have a generator availability index for them, MVAr availability, but if necessary, we could add that in the future. And also the final index is a loss of load index, which is a ratio of the actual critical load supplied divided by the total critical load. So these are other three indices that we kind of combine with the topological factors that we've seen before. So all of these indices are again combined using an MCDM technique. In this case, since we are only combining 4 different metrics, we use a simpler technique, which is the AHP, which is the analytical hierarchical process. Excuse me. And the individual indices are first normalized and then combined, as we said before. And the CyPhyR formulation, which is for this network at least, is we've tried to make it a more analogous comparison, which is to say it is we tried to have like a one-on-one mapping between the physical and the CyPhyR resiliency. So you have the network configuration on the physical network, and you have the network configuration on the communication network, and we have a similar sort of metrics that are derived from both of these systems. For the physical resiliency, you have the number of hops or the number of segments that the power has to go through before going from the source to the destination. And in the CyPhyR resiliency, we model that, or we draw a parallel to the number of security mechanisms that you have to gain, or the number of security privileges that you have to gain to go from point A to point B. And the vulnerability in the lines, or the BVI index, that tells you how repetitive a particular segment is. We model that, or we draw a parallel with the number of possible attack paths and the vulnerabilities or the attack path that repeats, or the step that repeats in the attack paths. And again, in the megawatt availability, we compare that directly with the available bandwidth in the network. The megawatt, we compare that with the latency of the network, and the loss of critical loads is we kind of compare that with the state of the device, which is to say, if it has already been compromised, then we consider that to be a loss per se, and the other loads or the other devices are still functioning. So this is kind of the framework that we have for the CyPhyR resiliency. We're still working on that framework, still working on trying to generate results and validate that particular CyPhyR resiliency framework, but this is the direction that we're heading in. And just to touch base with what the rest of our team is doing at Rutgers. They are focusing on device level resilience quantification. So you have a PLC or a controller that's sitting in your system, and you have to verify if that particular device is working as you want it to be. And what we do is, excuse me. So what we do is so in the next slide. So we have something called a TSV that sits between the instructions that is coming into the PLC, and it basically disassembles the executable into IL code, the intermediate language code, and then it creates an automated temporal execution graph. And based on the graph, we see if the if there is any violation in the instruction that is coming into the PLC. So this tool has already been delivered to Siemens, and we've heard about it in the last industrial workshop, and the demonstration has also been shown. So the problem with the controller level logic protection is that the firmware itself can be infected, and there is no way to understand if there is a problem with the firmware itself. So even a resilient control logic cannot ensure the PLC's output integrity at this point. So which would again result in the power system operation being impacted. So the new effort that's going on right now is to ensure the resiliency even despite ongoing control logic or firmware attacks. So this controller I/O verification would basically look at the outputs or the output of the controller, and then it would drive it towards a safer state, which might not be optimal, but it would definitely not damage the power system. So it would drive the system's operation towards a safer state by verifying the controller's output module. So that is our overall our approach towards controller I/O verification. And so just to come back and round it all up, this is sort of our big picture framework. So we have a transmission level. So we've already presented a couple of meetings ago our efforts about federation and combining these different tools together. So this is how these various pieces fit together. So we have, say, the transmission system in different system softwares, such as Opal RT, and we also have a transmission system communication model. We have its associated EMS system, the energy management system, and we have multiple distribution systems combined with the microgrids if necessary, and these are federated across different simulators. And we have different resiliency tools that kind of measure the resiliency for each of these individual systems. The transmission system tool, the CyPhyR, the CP-SAM tool. We have system tools for the distribution system. So we would exchange data between all of these different tools, and the overall goal is to study the resilience or the changing resilience for different scenarios across all of these systems combined. So what happens if there is a fault in the transmission system? So how is the transmission system resilience changing? And how is that change in resilience affecting the distribution and the microgrid systems? And again, also going from bottom up, how is the change or a sudden load increase, for example, say in the distribution system, how would that affect the transmission system? And how is the resiliency changing across these different systems? So this is our sort of big picture validation that we are kind of building towards. And I believe that's the last slide. And that's it. Thank you.
Thank you, Venkatesh. Do we have any questions? Al, you always have a question.
All right, I have a question.
Al has a question.
So Venkat, with distribution systems and also increasingly microgrids, they're going to models that like 61850 process bus and station bus. How does that affect your reachability? What was the reachability index or reachable device or whatever calculation?
Right. So I'm not quite sure if, for example, I'm not quite sure if the protocol itself would have much of an impact. So we try to be agnostic of that. So the reachable devices would be more in terms of what security privileges would you need to go from one node to another node. Let me just go back to the slide to see if that helps. Okay. Oh, jump too far. So, for example, if this is just a generator, right? So it has different, it might have different protocols or different ways of communicating within that particular node, and it might have a different protocol that communicates outside the particular node. But the reachable devices is just a way of including the security privileges that exist between these different systems. And if the attacker compromises certain, say, a firewall, so that would increase the number of reachable devices that the attacker has access to. So I'm not quite sure if that answers your question.
Yeah, we're wrestling a little bit with this kind of thing too. I'm thinking, for example, if you have IEC 61850, that a number of devices can subscribe to goose messages from other devices. So is that reachability? I think you have to find some vulnerability in goose.
Right. I think that would be, so there would exist a communication channel between, say, the PUBs of devices, but you would have to have some sort of an elevated privileges to actually manipulate or compromise the operation. So that is, again, I think if the security privileges are compromised, then I think the reachable devices would increase. But in my opinion, at least, just because two devices are connected, or if there is a network link between two devices, that would not add inside the reachable machines. It would just be it would just be a network connectivity, but the reachable machines would only increase when you have the access that you would need on that particular machine.
Right. It seems to me that in general, if you compromise a device on a 61850 bus, that you can publish incorrect goose messages or whatever.
Right.
But it's not obvious that you can compromise another device on that bus just from owning that one, the initial device.
Right. I agree. I agree with that statement. Yes.
Okay.
Do we have any other questions from outside of this room?
I have a question, Trisha. This is Dilhan.
Hi, Dylan.
Hi, how are you, Venkatesh?
Oh, I'm good. Thank you.
By the way, very well delivered presentation. Thank you for that. I'm quite aware of the Rutgers portion of it. About the Washington State side, who would be the intended consumer of the tools that you explained to me? Right.
I would say various utilities or various utilities. So I'm not sure so we have another project with another in another project. We are working with the Alaskan grid in the core urban distribution system. So they are interested in having metrics that quantify resiliency. So I would imagine other utilities in this line would be similarly interested.
Okay, so when you mention utilities, and you also mentioned that these are sort of real-time metrics that are coming out of this tool, is that right?
Yeah, that's right.
Okay, so in that case, is it intended to be in a control room for the control room operators to actually look at it, or is it going to be sort of like a back office system controller assistance center people who will be looking at it? Like that was my question. Like when I asked who was the consumer.
Sure. I would imagine this to be so the main purpose of this tool is to enable better visibility and better awareness for the operator. So I would imagine there's two scenarios. One is, which is kind of like a safety scenario, would be you can use this tool for operator training, because you can simulate various cyber attacks, and you can simulate various other failures, and you can see how the metric would change over time, and you can use it to train the operator to respond better or more effectively in face of a changing scenario. And if it's to be deployed out in the field, again, I would say that this is more of an operator visibility or an awareness tool. So we are specifically positioning it not to be a control mechanism, because any device or any technology is fair game for a cyber attack. So we are aiming, or we are positioning this as more of an operator visibility or an awareness tool. So it would sit in the control center and help the operator make better decisions.
Okay, so have you guys engaged any of the local utilities or any utility within that area to get their feedback? Like, how did you actually come up with the concept that this is what the people need?
So I'm not sure if I'm completely qualified to answer that question, but this has been an ongoing research for close to 3-4 years now. So we've talked with different utilities that we've worked with before, including our local utility here at Washington State, and as I've mentioned, we've talked with. So this is also been kind of implemented in Idaho Falls in collaboration with Idaho National Lab. We had a student of ours work there. And also, like I mentioned, the Alaskan grid is another example. So we've talked with different utilities to kind of understand what is their need, or how we can fulfill their need best. So we do not want to go towards an approach where you would have a large number of, we don't need many metrics, because the operator does not have enough time to kind of understand everything that's going on. We thought it would be simpler to just have one metric that the operator can look at and maybe have further details if and when he or she needs it. So we do have some industrial involvement that's been going on in this project. So we've kind of leveraged our experience with different projects to create this framework.
Okay, good answer, because I was getting to that point where if you overload with multiple matrices for the control room operators, those guys, I've been in control rooms. They have, I'm sure you're aware, they have multiple things to keep looking at. If you keep adding more and more, they're just going to ignore. I've seen operators actually ignore stuff. So that was a good approach that you took. Thank you.
Right. Thank you for the feedback. Yeah.
Any other questions we have?
Yeah, hi, Venkat. This is Pete Sauer. I came in a little late, so maybe you already mentioned this, but do you have a feeling or any results on the sensitivity of the resilience metrics to different options in a design, like the communication design or the power grid design, to improve the resilience if it doesn't meet some minimum?
So if I'm understanding your question correctly, I think you're asking about using these metrics to better design the power systems and its associated communication or other systems, right?
Right.
Okay. We haven't actually, at least in terms of CREDC, we haven't actually, tried to study that, like designing or enabling resilience through these metrics, because we focus more on creating awareness and maybe creating different. Yeah, I would say more about creating awareness for different scenarios, but I do see that as something that we can do in the future, which is to use these metrics to design more resilient power systems. And I'm sure that there is another project that we're doing here at Washington State that is building towards something like that, but I'm not completely aware of those efforts, so maybe I can get back to you with an answer on that. But yes, we do want to enable that too, which is to use these metrics to kind of design resilient power grids.
Okay, thanks.
Thank you, Dr.
Okay. Any other questions that we have? Going once. All right. Thank you, Venkatesh, very much for a great presentation.
Thank you.
Yes, absolutely. Just a couple of reminders. We don't have meeting next week. Happy Thanksgiving. And then I believe, I don't have the schedule in front of me, but I believe we pick up after that. And Linda will be sure to send out notification. And we also will be having a seminar scheduled, I believe it's December 11th, so pencil that in on your calendars. We'll be sending out more information the next week. Other than that, that is it. Thank you.